Hi guys, so today we're going to talk about the Doppler effect. A few more things before we get to that. Um, so you see how sound here can be produced, different way it can be produced. And then, interestingly, we as human only can hear a very small range of frequencies. So when we are newborn, like a newborn baby, can hear from 20 hertz to 20,000 hertz. And then we can damage our eardrum. Maybe we're going to be less sensitive to the low frequencies and less sensitive to the high frequencies. And as we get older, everything gets stiffer. So it's going to get harder to hear about 15,000 hertz, right? So it means the eardrum has a hard time to, 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 to catch on the very high frequency, right? It's not going to vibrate fast enough. So as we get older, maximum might be like 15,000 hertz. If you listen to very loud music with the earpod, so you're gonna damage your ears, and of course that range will decrease. So below that, you have what is called infrasound, below 20 hertz. Above 20,000 hertz, it's called ultrasound. And we have a lot of application in technology with ultrasound, and we're going to see that in this today. A lot of animals use those sounds here, and including dogs. For example, you have those special whistle with very high frequency, and the dogs don't like that very much, even though we don't hear that. Another thing that is interesting is that our ear is not responding equally for all the frequencies. So for example, if you have here, as measured by decibel meter, let's say you are at the threshold of hearing, okay, so that's going to be intensity of 10 to the negative 12 watt per meter square. You see, at low frequency, you're not going to hear anything. And then you start hearing maybe there at 500 hertz, 1000 hertz, you're going to hear. And then above those frequency here, you will be able to hear. Now, if you are at 20 decibel, you see that below 20 hertz, you are not going to hear that. Okay? So how loud we perceive a sound depends on the frequency. So if you are at 100 hertz, for example, we're going to start hearing if the sound is loud enough, right? Maybe 30 decibel. If the frequency is 40 hertz, we're going to start hearing if the sound is at 60 decibel, for example. Okay? So the loudness as perceived by us depends on the frequency. And there was a nice video on YouTube, and
Here's a crazy life hack everyone needs.
it's not this one, it's this one. So have to be careful with your ears. So here it's the same frequency and same amplitude, okay, same intensity. So same intensity, not same frequency, sorry. So it's going to be the same intensity, okay, for all those frequencies, and the frequency is going to change. So if you are very young and you didn't damage your eardrum, you're going to hear from 20 to 20,000 hertz, but the sound will not be as loud for all the frequencies, even though it's the same intensities. So it depends how we are it's a matter of perception. So the same intensity, different frequencies. So I don't hear anything. I don't hear anything. You might, I don't know. I don't hear anything. I start to hear. So you see how the loudness as perceived by us is going to change as a function of frequency, even though the intensity is the same. Isn't that interesting? So you see that I'm old because I start hearing about around there 150 hertz and I stop hearing after 50,000 hertz. So I will put the link in the description. So I think it's a great video. It's a great video indeed. Okay, so that's interesting, especially if you are health science major. So again, this slide comes from the book Johnson and Cutnell. So you have a lot of application with sound. So for example, you can use pulses of ultrasound. So ultrasound, okay, has a very high frequency. High frequency needs large energy. So the energy of the wave, the intensity, remember, it's the energy carried by the wave per unit second, per unit area. So let's say there is an area here. So if you have the intensity of the sound and you have of course, it depends on the distance to the source, you can find the energy delivered here to that kidney here. And why do they use ultrasound? Because ultrasound has a high energy, so high frequency means high energy. So it's going to break those stones here that will be able to go through. Okay. So there is a relationship that I was mentioning before. There is a relationship between intensity. So last time we talked about intensity, the frequency and the amplitude of the sound wave. Okay. So if I increase the frequency, so remember that waves, sound wave, you have those air molecules that are going to vibrate. So let's look at those particles here. So you see how they vibrate? So if I increase the frequency, they're going to vibrate faster, right? So if they vibrate faster, that means they have more kinetic energy. So that means the wave is carrying more energy. It also depends on the amplitude, of course. So if it has a large displacement about the equilibrium, it's also carrying more energy. So let's see if I increase, you can even play the tone. So I increase the frequency. So they are moving faster. If I decrease the frequency, they're going to move slower when they settle down. You can also decrease the amplitude. Or we can increase the amplitude. So remember, it's a pressure wave. So the intensity of the wave, it's going to be equals to, so now I'm confused. So my point was that the energy carried by a wave also depends on the frequency and on the amplitude. So it means the displacement of the particles about their position of equilibrium. It depends on the frequency square. So that's why if you want to break down stones in the kidney, then it's advised to use ultrasound. That's the idea. So they need to have large amplitude to increase the energy, because intensity is proportional to the amplitude square, and they need to use high frequency as well. Not too high frequency, because you don't want to destroy the kidney. You just want to have the high frequency. And you can use also this procedure here to break blood clouds. Okay, so another use for ultrasound, of course, is to see inside the human body, because the sound will be reflected of tissue here, and then you have a computer that will get an image of the inside. So this is called tomography. Another application here, you can use ultrasound to destroy a tumor if it's not far from the outside. So here it will be like a brain tumor. Okay, you have also other interesting applications that you can look it up here. So they have these special refrigerators, fridge, and what they use, it's a very high technology that they use. What they do is that they make a standing wave. Do you remember standing wave? So they have a speaker and they make a standing wave, and that standing wave, it's going to take the energy from the fridge and dump it outside. And it use that because they send that standing wave in helium, so it's going to compress it and then expand, compress, expand, right? So when you have a compression, it's going to heat up, and expand, it's going to cool up. So that way, it's going to take all that energy here, all the heat, and remove it from the fridge. So it's a very advanced technology. You can look it up. So when the gas expands, it absorbs the heat from the fridge and release it to the outside environment. You have another technology here where also they use ultrasound. So the energy of the ultrasound here in that case turns into temperature and light. So I have a website here if you want to look it up. So let's go to the Doppler effect, which is very interesting. So Doppler effect happens when there is apparent shift in frequency, because there is a relative motion between the source of the sound and the observer. So for example, if you have a car or a train or ambulance, making a lot of noise coming towards you, it's going to make something like, ew. So high frequency, low frequency. Okay. And let me show you why first. So let's look at the concept first, and then we will do the math. So here, I will put the link also in the description. It's a nice cartoon. So this is the source of the sound. Okay. So what you see here are the wave fronts. So we talked about wave front. So you have a crest, a throw. So it's like the wave. Okay. But you are looking from above, right? So it's going to be high pressure, low pressure, high pressure, low pressure, high pressure. So it's a longitudinal wave, and that's the source of sound. Okay, sound is not instantaneously getting to the observer. So this is the source, and this is the observer. So it takes time. So the observer is not moving, the source is not moving. So every second, he's gonna be hit by so many wavefront, right? So if you have, for example, 40 wavefront per second, or 40 crest, or 40 cycles. That will be a frequency of 40 hertz. So he is emitting at a frequency of 40 hertz. This person is going to hear at a frequency of 40 hertz. So 40 cycles per second. Now, what's going to happen if the observer is moving toward the source? So now it's going to pass through more wavefront, right? So that means more wavefront is going to pass him. So it means he's going to perceive a higher frequency. Okay, so let's look at that again. So now he's going to move. See? More cycles per second, more wavefront. And now he's moving away from the source. And you see, it's going to be hit by less wavefront per second. So that's going to happen. What's going to happen is going to be high frequency as he moves toward, low frequency as he's moving away. Okay. Let's look here an example. So definitively, you see when it's moving away, we perceive a lower frequency, lower pitch. If it's moving toward, we perceive a higher frequency. Definitively lower frequency. Then, okay, so I have to skip the...
Let's say you're writing an important email to your boss, but you don't know where to start. Here's what to do.
Okay, same thing. Now, there is this show, very funny show. It's called The Big Bang Theory. And one of the best episodes is Sheldon explaining the Doppler effect, because he goes to a party, a costume party, and his costume is the Doppler effect, right?
No, it's not.
If I have to, I can demonstrate. So what time does the costume parade start?
The parade?
Yeah, so the judges can give out the prizes for best costume. You know, most frightening, most authentic, most accurate visualization of a scientific principle.
Oh, Sheldon, I'm sorry, but there aren't going to be any parades or judges or prizes.
This party is just going to suck.
Oh, come on, it's going to be fun, and you all look great. I mean, look at you, Thor, and oh, Peter Pan, that's so cute.
Actually, Penny, he's wrong.
I'm Peter Pan!
I got a handful of pixie dust with your name on it.
No, you don't. Hey, what's Sheldon supposed to be?
Oh, he's the Doppler effect.
Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Oh, sure, I see it. Now the Doppler.
And he has the high definition, so I will put the link also in the description. So let's see here. So again, you have the observer here, and you have the source. If the source is stationary, then the frequency perceived by you is the same as the frequency of the source. Now, if the car is moving towards you, you're going to be hit by more wavefront per second, right? So the frequency that you're going to hear here is going to be higher. So the wavelength here will be smaller, higher frequency. Now, for someone sitting here, I don't know why it's not showing. Here we go. So someone located here you see that the wavelength decreases, okay, because the source is moving away, right? So you will have less cycles per second, so the frequency will be lower. So lower pitch, higher pitch. And then we're going to see that in the next lecture. If it goes as fast as the speed of sound, then you're going to have a shock wave because all those wavefronts are going to pile up. And that's going to be, that's going to hurt a lot. Okay, so the Doppler effect, as Sheldon explained very well, is a change in frequency of the sound detected by an observer because the sound of the source, the sound source or the observer have different velocity with respect to the medium of sound propagation. I found the definition of Sheldon better, but you get the idea. So what's the equation for that? So the demonstration is in your textbook, so Johnson and Kutney, but let's go to the equations right away. And let me tell you how to memorize them. So you see, if the source is moving toward the observer, and here we suppose that the observers are not moving, only the source is moving. So if it's moving toward, so you're going to perceive a higher frequency. So is it a minus here or a plus? So here at the denominator, you have 1 minus, and that number here has to be smaller than 1, because that's going to be the speed of the source, and that's going to be the speed of the sound. Okay? So the speed of the source is smaller than the speed of sound, otherwise we have a shock wave. So that's going to be smaller than 1. So that's going to be smaller than 1. So that's going to be larger than 1. Okay? So if you have a minus, it will decrease the denominator. So it's going to increase that number here. So you will have higher frequency. If it's moving away, so if the source is moving away from the observer, you want to have a plus, because 1 plus something even smaller than 1 is going to be larger than 1. And 1 over something larger than 1, it's going to be smaller than 1. So it's going to be 0.8, 0.7, 0.6. So you get a lower frequency, larger wavelength. Okay? Oh, I forgot to show you, there is also an app. I had the app somewhere. My app is gone. It's fine. Okay, so let's try to do this one. It's just plugging in. But I can show you how to plug it in your TI. I have my TI here. So let's see. Very simple problem. So let's identify everything. So that's going to be called, so the source. Okay, so we're only taking the cases where the source is moving. Okay, so that's the source. And that's your frequency, but that's the frequency of the source. So that means that the frequency of the source is 414 hertz, and the speed of the source is 44.7, and V will be the speed of sound. That's going to be 344. So you have the train here, and it's making some noise, and it's moving. So it's the source. So it's moving toward an observer. So the wavefront will be hitting him faster, right? So we expect to have a larger frequency. So we know that in that case, the frequency perceived will be larger than the frequency of the source. So we need a smaller denominator. So that means the frequency of the observer will be E equals to the frequency of the source. And here I'm going to have 1 And then here I have 1 minus the source over the speed of sound, right? So you take your calculator, and the easiest way to do it, you start with the denominator. So it's going to be 1 minus source is 44.17 divided by the speed of sound is 344. Enter. And then you take the reciprocal. So I take the reciprocal. Okay. And then you multiply by the frequency 415. And it's going to be 477 hertz. So you have to check that indeed this is larger than the 415. Now, if it's moving away, so if the observer is here, so it's moving away, so then we have observer equals 415. That's going to be 1. And here we have a larger denominator to make it that smaller, to make it smaller. So you use the same trick here. Calculator. You do 1 plus the speed is what? 44.7. 344. Take the reciprocal and multiply by the frequency. So 367. Okay. But this case is only when it's the source moving. Okay. Tu vois, Molly? Molly? Okay. So next, I think it's the same thing, but toward you. Okay. So it's the same kind of problem here. So let's do that with the calculator. So if it's moving towards, that means there is a minus here. Okay, so you can start with the denominator. So it's going to be 1 minus the speed, the police, divided by, let's say it's 344. Could be 340. It's not going to make a big change. Okay, you take your reciprocal. Okay, and then you multiply by 1600 and you get 1725 hertz towards. And it's good because it's larger than this. Now, if it's moving away, you're going to use that here. So it's going to be 1 plus 25 divided by 344. Okay. Take the reciprocal. Okay. And then you multiply by 1600 and you get 1492 hertz. Okay? So it's not, it's not bad. It's easy. Okay, let's try to do this one, number 6. It's a little bit different. So let's see if we can do that. A bird is flying on an emitter frequency. So that will be the source. Okay. Again, it's the source that is moving. So he hears a higher pitch. So that will be the observer. And they want to find the speed of the bird. So that will be the source over the speed of sound. So first of all, if it's a higher pitch, that means that the equation to use is going to be equals to observer it's going to be the source, so it's going to be 1250. And then you have a minus here, minus V sub S over V, no? So it's going to be 1290. Okay, so now we want to solve for this here. So this is really not bad. Okay, you can divide both sides. So we have 1290 over 1250 equals 1 over 1 minus Vs over V. So then you flip everything. So 1250 equals 1 minus Vs over V over 1. Okay. So that's going to be, right. So that's going to be Vs over V equals 1 minus the ratio here. And that's going to be equals to 0.031. So you can do the computation. So Vs over V equals 0.031. So in percentage, that's going to be 1, 2, so 3.1%. So it's a little bit different. So, but it's mostly algebra. So I think we're gonna skip this one because it's the same equation that you are using. The only thing here, you have to convert to meter per second. So 30 kilometer is 30,000 and 1 hour is 3,600. So you have to divide 30,000 by 3,600. So again, I got those problems here. I will put the link in the description from a website, this website here. So it has great examples. That's for the AP physics. So let's do a conceptual question here. What do you think of this one? So if they are moving in the same direction, that means there is no relative speed, right? Because they are moving at the same speed. So if there is no relative speed, so that means there is no shift in frequency. So then the answer will be that one. Okay, let's keep going. So now we have seen the case of a moving source. So what's going to happen if now the observer is moving? So if the observer is moving toward the source, he's going to perceive a higher frequency. If the observer is moving away from the source, a lower frequency is going to be perceived. And again, you can look at your textbook, but these are the equations. It's easy to remember because here, if it's moving toward the source, you expect a higher frequency. So then that's going to be the plus here. If it's moving away from the source, you expect a lower frequency. So that's going to be the minus. So here is an interesting one. That's the idea of kind of echolocation. But in addition to that, you can measure the shift in frequency. So there is a source here that makes a noise, right? A sound wave. That sound wave is going to reach that object. Okay. And then it's going to be reflected. So it's like echolocation. But that object is moving toward the source. So already the perceived frequency will be higher. Okay. So then the source here, the object here become a source itself at the frequency it was the object here is going to reflect that sound wave, but at the frequency that it was getting here. Okay, so this problem here is interesting because it goes in two phases. So here you have a source of sound, and here you have the observer, and the observer is moving toward the source. So as perceived by the observer, there will be a shift in frequency. The observer will perceive a higher frequency. So that means we're going to use that equation here. But then it works like echolocation. That sound wave is going to reflect off the object. So the object is becoming a source itself, okay, with the shifted frequency. And the source now is moving towards the detector, okay, because this is a source, but it's also a detector. So now you have a detector here, and this is the source. It's moving toward. So there is an additional shift in frequency. So this is called the double effect, double Doppler effect. And so we have to do it in two steps. And I will show you the equation after. So step 1, phase 1, okay? So this is the observer here, and this is the source. So which one is moving? It's the observer, okay? So the observer is moving, and you see that the frequency perceived by the observer has to be larger than the frequency of the source because it's moving towards. So because the observer is moving, I have to use one of those equations here. And because I expect a higher frequency, I'm going to use this one. Okay. So you can pause the video and try to do this. So it's going to be F perceived. The frequency perceived by the observer is the source. And the source is, I forgot, is 5,000. So it's going to be 5,000 and has to be a plus 3.5. And the speed of sound, let's say it's 344. And you can do that with your calculator. Take your time, and it's going to be 51 hertz. And that's good because this is larger than that. Okay. So now the wave has reached this object here, and it's being reflected. So now this is becoming the source. So now we have a source. So this is the source. And here we have the observer. So now we have the source here, which is 51 hertz. And it's emitting. Okay. And it's moving. So now it's the source moving. So the source is moving. And the final frequency that you're going to perceive here, that will be detected here, has to be larger again than the source because it's moving towards. But because it's the source moving, I have to use the other equation. So now I have to say, so that's frequency here. Now I have to use the other one, which is 1, it's towards, so it's minus 3.5 over 340. Okay. So this is kind of echolocation, and the police officer, they have a gun that will produce sound, and And that's how they can find your speed. If you are over the speed limit, that's the idea here. So if you do that, like I showed you last time, with your calculator, say you start with this, so 1 minus 3.5 divided by 344. Okay, you do minus 1. Okay, you multiply by 51. Okay, and you have 5102. 5103 hertz. Okay, so it's like you shift and then you shift again. Okay, so that's the final answer. Now, maybe we can find an easier equation. So F0 prime equals this. But this was that, right? So it was 5,000 times 1 plus the speed of the source over the speed of sound. Okay, so I replace this, so this equation into here, times 1 over 1 minus V sub S, the source over V. So if you can make it some cosmetic here, so you can put at the same denominator, so V plus Vs over V minus Vs. Okay? Yes. So you can have that. And then you can do some algebra, and then you can extract the speed of the source as a function of the frequency perceived. Okay? And then you can find the speed of the source, right? Okay, I think that you have to check, okay? But I think that you have something like this where you have to subtract observer minus the source, the original one, so the 5,000, then you add those frequency times V. But you have to check, because I did it quickly. So this is Fs. But my point is that using that method, then you can find the speed of an object. So this is how, for example, you have, you can use that for a weather purpose. So you send, for example, that will be a microwave actually. So here they use a microwave, not a sound. And you see how when it's bouncing off, there is a shift in frequency. By finding the shift in frequency, you can find that speed here. And actually, the police officer, I don't think they use sound. They do not use sound. So sorry, that was my mistake. They use a microwave. Okay, so you see someone is coming here. The wave is going to bounce off. There will be a shift in frequency. And using that shift in frequency, the computer will find the speed of the car. Okay? So using microwave. So in that case here, that technology here in sound in medicine. So in that case, yes, they use ultrasound, I think. So you see here, there is a reflection, and these red blood cells are moving, and you can find the speed. So that's the idea is the same as this one. You can find the speed. Okay, other application here, which is a very nice one, with a special kind of ultrasound, but the same idea. You can see things moving. So you can see the baby moving, but you can see also the blood here in the heart. So you combine the technology of ultrasound and the reflection with the Doppler effect. And we can monitor the heart or blood flow just by using the shift in frequency of the ultrasound. Okay? So we're gonna go back to this next time because you also have a Doppler effect for light or electromagnetic wave. So in this case here, they are not using sound, they are using microwave. Okay, so now you can combine both. So you can have both the source and the observer both moving. So in that case, you're going to use this equation if they are both moving. So just, I found the website here. So in that case, the source is not moving, the observer is not moving, the frequency does not change. There is no shift in frequency. In this case, it's the observer moving toward. So we're going to use the equation with 1 plus Vs over V. And then the observer is moving away. So the equation will be, if you go back here, the equation will be this one. It's moving away. See, it's moving away. So the shift of frequency means that the frequency will be in the lower pitch. So what's going to happen here? Let's see. Now we have the source moving. So higher frequency, perceived lower frequency, because the observer is being hit by less wavefronts per second. Okay, so in that case, we use the equation with the denominator. Let's see what's going to happen here. So they are both moving. That's what we're going to see here. If the observer and the source are both moving at the same time. So in that case, we use this equation. So you have the source and the observer, and they are both moving away from each other or toward each other. So if the observer is moving toward, we expect a higher frequency. So we use the plus. If the source is moving towards, so we expect a higher frequency. So we use the minus because it's at the denominator. Okay, so smaller denominator, larger frequency. Okay, so if it's moving away, we expect a lower frequency. So if the observer is moving away from the source, that will be a lower frequency. So it's going to be a minus. If the source is moving away from the observer, so we expect a lower frequency, so that's going to be a plus. It's not very interesting here, it's just algebra, but that's what's going on here. They are both moving toward each other, so higher frequency, and they move away from each other, so that's going to be lower frequency. Okay? And that will be something that we'll do next time. What's going to happen if the source is moving faster than the speed of light, the speed of sound. So if the source is moving faster than the speed of sound, you see that the observer cannot hear anything. He's good. Even though this airplane, for example, reached the speed of sound, so there is a sonic boom, but not yet, not going to hear anything. You see all the wavefronts here are piling up. Nothing can be heard. And here, that's going to be hurting a lot. When those piled up wavefront is going to cross over you. Okay? So that's combining. So let's do this problem. I have one problem with this. I just, I think here. So let's try to do this one. So this one, you have to remember the equation, but hopefully you are given the equation. That's much better. Yeah. Or you can remember. It's not too hard to remember. So this is the source. The source is 1000 hertz, and they are moving toward each other, the source and the observer, at a speed of 100 meters per second. So the speed of the source is 100 meters per second, and the speed of the observer is also 100 meters per second. So we start here by the observer at the numerator. So F perceived will be the source, so 1000, and it's moving toward. So I expect a larger frequency. So that means I need to use a plus here. So that's going to be 344. That's going to be plus, and then 100. So at the denominator, the source is also moving toward. So I expect higher frequency, smaller denominator. So I need to have a minus 344 minus 100. And you see we get same equation here. You can think about it. Why is that? So let's go back to here. Okay, and you do the computation, you use your calculator, and the answer is about this. So that will be the answer. Okay? So in your book, so this one comes from your book, Johnson and Kirknell, and they do it this way. But if you do some massage here, you will get that equation, you will get the same equation. And again, remember that the intensity of a wave, so that will be the energy. So unit is watt per meter square, okay? Depends on the frequency square, because higher frequency means larger kinetic energy, and the amplitude here. And that amplitude here, in this case, will be the displacement of the molecules about their equilibrium position. But if the displacement is large, then the pressure also is large. So anyway, you are given the displacement of the air molecule, and they ask you to find the intensity. Okay? I don't think that's going to be a problem for AP or the MCAT, unless they give you the equation. But you see, you can get the intensity. It's going to be 2 times the density of air, which is 1.3, times the speed of sound. In that case, is 343 times pi square times the frequency. So it depends on the frequency, which is middle A square, times displacement is 0.13 times 10 to the negative 3. And there is a square. So you see the intensity is proportional to the amplitude square. That's why I told you if the intensity is divided by 4, the amplitude is divided by 2. Okay, we discussed that before. If you look at this sound here, you can see the graph, and you see how the amplitude is decreasing. That's because the energy is spreading over larger area. Okay, and if you get that, you plug that into your equation. I got 28.8 watts per meter square. That's a lot. Because the threshold of pain is about 10, or sometimes it's 1, depends who you ask. 1 starts to be painful. So if we want to know the decibel level, intensity level, it's going to be 10 log 28.8 over 10 to the negative 12, and you get 135 dB. And that's painful. If we go back to here, 135, 140, so that starts to hurt. Threshold of pain will be 1. This is 100. So here I am almost 140, so definitively hurting. Okay, so that's it for today. Next time we'll talk about shock waves and Doppler effect for light.